I'm going to go through the answers to the first 5 problems, and hopefully as you watch me do this, the idea of system schema or how to do system schema and free body diagrams will become more clear. Now remember, our overall goal is to determine when a system is in equilibrium or not equilibrium, because that will then tell us how we can, the set of equations and assumptions we need to make in order to solve a problem. So we're starting like with the very basic part of being able to figure out how to solve problems. And remember, for equilibrium, we have a observation and we have conditions. So our observations is that either our velocity is 0 or our velocity is equal to a constant. And our conditions is that the left forces equal the right forces, or the up forces equal the down forces. And we are going to determine, we are going to use the system schema to find all forces. And we're not going to put in, the primary purpose of the system schema is people want to put in extra forces, and so our system schema will help us to not have extra forces. And then non-equilibrium, even though that will be the next unit, our observation is that the velocity is changing and that the forces, like the left forces, are not equal to the right forces. I'm on the edge, so sorry, I'm writing really tiny. Or the up forces are not equal to the down forces. Okay, so that's what we're going for. So draw a force diagram for the motionless cat on a rug. And right here, we're going to notice that the cat is motionless. And so that tells us that we are in equilibrium. And so we need to make sure that forces balance. So we're going to label the forces and use equality marks for pairs of forces that have the same value. Now, I know the instructions are not written on here. I told you verbally. I keep forgetting to put them in year after year. So first we want to start with a system schema. So if you did not do schema for 1 through 5, definitely do them for the remaining ones. So our schema, we've got a cat, we've got a rug. We're going to assume that there's a floor. And we're also going to assume that we are on Earth, that the cat is not floating somewhere out in the universe. Okay. So between the rug and the cat, we have an interaction. Oops, I have no idea how that got to be there. Rug and the cat, we have an interaction. And this is going to be our perpendicular force. We also have an interaction between the cat and the earth, the rug and the floor, and rug and the earth, floor and the earth. And if you want to label it, the interaction between the cat and the earth is the weight. We also look at this and we see that we want the force diagram for the cat. And so we should put our boundary markers around the cat. And we are now ready to do the free body diagram. So we're going to represent the cat with a dot. And the first thing we need to do is figure out how many arrows do we put on the dot. And we look at the system schema and we count the number of forces that are breaking the boundary around the cat. Okay. There are 2 that are breaking the boundary around the cat, and so we're going to have 2 arrows on the cat. And so 1 arrow is the weight going down. And we know that the cat is motionless, it's in equilibrium, so our perpendicular force is the same length. So we've got a pair of vectors. You can only put congruency marks on pairs of vectors. We have a pair of vectors that are the same length, and so we're going to put a congruency mark on them. All right, that is number one. Number two, so we're going to read through, and we see that the skater is moving at constant speed, and we want to draw a diagram for the skater. So constant speed tells us that we are in equilibrium. And so we've got the skater. Now you might want to do skater, skates, ice, but I'm going to assume that the skates are part of the skater. So I've got a skater. I've got ice. And I've got earth. So we've got an interaction between the ice and the skater. And this is the interaction that is perpendicular. I've got frictionless ice, so I do not have a second interaction between the skater and the ice. There's not going to be friction. Sometimes I can have two interactions, but there's only the one. And then between the skater and the earth, we have the weight interaction, and then we can also do the ice and the earth. I'm going to draw a boundary around the skater. Nothing else is interacting with the skater. Nothing else is touching her, and there are no long-range forces. So we only have these two interactions. So let's do our free body diagram. This is the skater. In order to figure out how many arrows, we look at how many interactions are breaking the boundary, and there's just two, so we only have 2 arrows. So we've got weight going down. And we know that she is not moving in the vertical direction, and so we know that up and down has to be the same length. So this is the perpendicular. The perpendicular is always perpendicular to the surface. If I have a tilted surface, then the arrow would go off at a different length. And because she is not moving in the vertical direction, so she's in equilibrium both horizontally and vertically. So in the horizontal direction, she's moving with constant velocity. And in the horizontal direction, she is not moving. So she's in equilibrium in both directions. But there are only forces acting in the vertical direction. There are no forces acting in the horizontal direction. So you might want to say, well, how is she moving? We don't know. It doesn't matter. We are only looking at this point right now. It doesn't matter how she got into motion or what happens to her eventually. It's just right now we know that she's moving at constant speed. There's nothing else interacting with her, and so this is all the forces there are. Okay, next one. Sorry, blue. Draw a force diagram for the softball player who is slowing as she slides into the base. Okay, so again, we should look at, so this is slowing. So we would say the horizontal direction is not equilibrium, but in the vertical direction, we would say that she's in equilibrium because she's not moving in the vertical direction. She's sliding horizontally. She's not like moving up off the ground or down into the ground. All right, schema. So we've got the player. We have got the ground. We have the earth. Okay, so interaction between player and the earth is the weight. We know that there is a perpendicular interaction between the player and the ground. So the ground is holding the player up, but we also know there's a force of friction that is slowing her down. So this force of friction is parallel. So friction is parallel. To the sliding surface. And I'm going to erase the one arrowhead because it always goes opposite the direction of the slide, of sliding. So if she's sliding forward towards the base, or to the right to the base, friction is acting to the left. All right, and we're doing a force diagram for the softball player. All right, so here's our dot. So as we look, we need to know how many arrows to put on it. As we look at the boundary, how many lines break the boundary? The answer is 3. Weight always goes straight down. Now, she is not moving in the vertical direction, and so the perpendicular force, and again, this is perpendicular to the surface. It's perpendicular. Because she's in equilibrium, we know that this pair of forces has to be congruent. And then the third force is the force of friction going backwards. Because she's not in equilibrium, we don't know how long this force is, so we're just going to draw it a random length. I don't have a pair of forces in the horizontal direction, so I cannot put a congruency mark on that. So I'm no congruency mark. I can only put congruency marks when I have a pair of forces that are equal in length to each other. Okay, draw a force diagram for a chandelier that is suspended from the ceiling by a chain. So we're going to assume that it is not moving. So we're going to say equilibrium in the vertical direction. Schema, we've got the chandelier. The chain has been specifically mentioned, so we've got a chain. We also have a ceiling. And then we always have the earth. Okay. All right, so the chandelier and earth, we have weight. Between the chain and the chandelier, that's actually a pull. And so this is a tension force, so we're going to put a T for that. And the chain and the ceiling is also a pull. So that is a tension force. The object that we are looking at is the chandelier. How many forces do we have breaking the boundary? We've got 2, so that means I have 2 forces. And so I'm going to have the weight down. Now, we assume that the chandelier is not moving, so that means that the tension force, which is going up, I've got a pair of forces, it's in equilibrium, so this pair of forces has to be the same. Now, some of you may be nervous that we don't have the perpendicular force, and the perpendicular force is a push, and so we don't have a push here, and so there is no perpendicular force. All right, last one. Draw a force diagram for the bucket of water that is being raised from the well at constant speed. All right, so we've got constant speed, so that means we've got equilibrium. So this is vertical equilibrium. Okay. All right, we've got a lot of things. So we have the person. Person is touching a rope. We also have a pulley. You do not have to put all this stuff in here. You really only have to put at most 3 objects if you want to. That's the minimum pulley. You could also put in the ground. We have a bucket and the earth. Now truly, since we are looking at the bucket of water, the only things that you really have to put in are the rope, the bucket, and the earth. So if you only did those three, no problem. All right, let's put down what's interacting with what. So the person is interacting with the rope, the ground, and the earth. And again, we have a pull on the rope, so that would be tension. We have a push on the ground, so that would be perpendicular. And then we have weight for the earth. The rope and the pulley are interacting with each other. That's a weird interaction. It is definitely a push, and so we're going to call that our perpendicular force. And then we've got the rope and the bucket, also a tension, it's a pull. And then bucket and earth is weight. We are looking at the forces on the bucket. So we draw our boundary. We've got dot representing the bucket. And how many forces or how many interactions do we have with the bucket? Only two. We've got weight going down. We know that it's an equilibrium, so that means the tension going up has to be the same. And I've got a pair of forces that are the same length, so I'm going to put on congruency marks. Okay, you should do 6, 7, 8, and 9. This other problem you will wait to do until Wednesday.